Differential equations, we're in section 4.7, the last section of this unit. We're on day 2, and today we're going to be looking at, as you see the top page here, non-homogeneous Cauchy-Euler equations. Ironically, we're going to get to that as example 2, but for example 1, we're going to have a higher order Cauchy-Euler equation, and actually it will be, in this problem, homogeneous. The right-hand side will be equal to 0. Now, yesterday we had second order Cauchy-Euler differential equations. Today we're going to look at a third order. But again, let's assume that we've got y equals x to the m. Take your derivative, you'll have m times x to the m minus 1. Next derivative, that power of m minus 1 comes down. You drop your power by 1. It's now x to the m minus 2. And finally, for a third derivative, drop down your m minus 2 out in front, subtract 1, and then you have x to the m minus 3. Right now, we're going to substitute that all in. However, we are not going to create a formula like we did in general, like getting a quadratic. When you have these higher order differential equations, Cauchy-Euler ones, it is honestly better to just substitute it in directly. You're going to see that with cubics, that's generally the situation that makes life the easiest. Y triple prime, we're going to have our m times m minus 1 times m minus 2, x to the m minus 3. That's y triple prime. Then we'll have minus 2x squared. But what about y double prime here? Well, you can just copy it right above. M times m minus 1, x to the m minus 2. Then we'll say plus 4x. But y prime is mx to the m minus 1. And then finally, we'll have a minus 4y. But even y itself is x to the m. And like we said, this is homogeneous. We'll have our right-hand side equal to 0. It's this first bracket here that is, without a doubt, going to be the most involved. And tell you what, let's just take a look at this m minus 1 times m minus 2. If you were to just FOIL that out, you'd get m squared, and a minus 1m and a minus 2m is a minus 3m. And then negative 1 times negative 2 is a plus 2. So you'd actually be left with that, wouldn't you? And then as you would distribute this m to that, you would be left with m to the third minus a 3m squared plus 2m. But then when we combine our x's, remember if we had x to the a times x to the b, you add those powers. And this is what you see every time with these Cauchy-Euler differential equations. The 3 and the negative 3 just cancel out. You're going to see every term here is going to have an x to the m. Likewise, as we come over here, as we distribute a m times m minus 1, we get m squared minus m. We can distribute that negative 2 in there, and as we do, we'd get a negative 2m squared. A negative times a negative is a positive. That would be a plus 2m. But x squared times x to the m minus 2, add those up, and once again, you'll have an x to the m. This next one is a little bit easier. You've got 4 times m. And of course, then we're going to see that, an x to the 1 times x to the m minus 1 is going to get you also an x to the m. Finally, we have this minus 4x to the m equals 0. And no doubt what you should be noticing right now is every single one of these terms has x to the m in it. Now, we could divide everything by x to the m and cancel that out. Or we could look at the right-hand side and say, look, the coefficient in front of x to the m on the right is a 0, so all of these other coefficients have to add up to 0. End of story is you get the exact same end result. You have m cubed minus 3m squared plus 2m. Then right here we'd have a minus 2m squared plus 2m. Then we'd have a plus 4m minus 4. And all of this will equal 0. And let's do some combining of like terms. Well, we've got a few 2m squared terms. This becomes a 5 minus 5m squared. We have a 2m, 2m, and a 4m. That's going to add up to an 8m. And then we'll have a minus 4. And this is what makes things a little bit different. We're not accustomed to regularly solving cubic equations like this that don't obviously factor. What you could do is see if this factors on the 89. That's always a real possibility. Let's just go back to what you did in AMA and in Algebra 2. We did some polynomial analysis. We said, look at your last term. A negative 4, what are the factors of 4? Well, a 1 or a 2 or a 4. What about your lead coefficient? Well, that's a plus or minus 1. You might remember we looked for P over Q, and those would be all of the roots that would be integers. Well, let's just try a 1 right here just to see. And now take a look at what we're going to do right here. We're going to do our synthetic division. You might remember doing this a long time ago. Always good to review some old material. We'll have our 1, negative 5, 8, and negative 4. And then we multiply. 1 times 1, that's a 1. Then we add. Negative 5 plus 1 is negative 4. 1 times negative 4 is negative 4. 8 plus negative 4 is a 4. 1 times 4 is a 4. This last term is a 0. And this is known as the depressed equation. This 1 now stands for 1m squared minus a 4m plus a 4. So you might remember doing this. Of course, our 89 can give us a great deal of help. You might think, well, what about the 1 right here? It clearly did work. You might remember the factor theorem. If a 1 works, if the 1 is a solution, then m minus 1 is, in fact, going to be a factor. And, if this 1 didn't work, then we'd try a negative 1. If that didn't work, we'd try a 2, and then a negative 2, a 4, or a negative 4. And our hope is eventually we find something that works. M squared minus 4m plus 4 is actually going to factor into m minus 2 and m minus 2. Like I said, the 89 can solve this also, but it's so good to have the skills to do this by hand. Solving, you'll see m equals 1, m equals 2, m equals 2. Here we go with duplicate roots. What about this 1 right here? Well, we could say that's c sub 1 x to the 1. How about the 2? Well, we have c sub 2 x to the 2. But then we've got that duplicate root. You might remember every time we had a duplicate root, we'd have an ln of x thrown in front. And there you have it. That would be your solution. As we keep going, as we take a look at example 2, now we're going to look at non-homogeneous Cauchy-Euler equations. The non-homogeneous implies, hey, the right-hand side is something other than 0. And we had 2 methods in Chapter 4. We can use the undetermined coefficients method, the undetermined coefficients, where we looked at our table and we assumed that y sub p was a general form. We'll get to that in just a moment. And we took derivatives and plugged that in. Then we did coefficient analysis. What else could we do? Well, we could use the variation of parameters with the Wronskian, where, of course, you might remember we'd have a u sub 1 prime would be w sub 1 all over w and so forth. So both methods are going to work. Both methods are good. One method is generally really preferred, and we're going to talk about that in just a moment. But here's where we're going to get you started for either method. you want to deal with the solution to the homogeneous solution. That's going to be setting that right-hand side equal to 0. And immediately you'll see it's a second-order Cauchy-Euler differential equation. So this is what we did last time. We could say, well, my goodness, this is really just review of our day 1 material. And that's great. We can very quickly get this thing solved. And always good to reinforce what we just did the other day. Here's a 3m plus 1 equals 0. Does this factor? Well, sure looks like it does. We have a 2m and an m. Let's try a 1 and a 1. Might believe everything's going to have to be positives here, and they are. You can double check. You have a 1m and a 2m add up to a 3m. Solving. Well, set that equal to 0 minus a 1 divided by 2. Here you just, get a negative 1. So we have our homogeneous solution right here. Whether we're using either of those methods, we need that. But here's what's going on. On this right-hand side, that is something that we could see from our chart. It looks like it's a quadratic, so we could say, you know what, let's just have a general quadratic. Take our derivative. So we're doing undetermined coefficients, which is great. We take our general derivative here, take a second derivative, that's just going to be a 2a. And then we go back and we say, you know what, let's just recopy this non-homogeneous. The right-hand side now would have your x squared minus x, and say, let's just see what happens when we plug this in. We're going to say, hey, plug that in for the second derivative. We'll have 2x squared times a 2a. We'll have here's 5x times, well, here's a 2ax plus a b. Here's your y, which is maybe the lengthiest piece of the puzzle here. We'll have our general quadratic form, and then we'll have our x squared minus x. So let's clean this up. We'll have a 4ax squared. As we distribute here, we'll have a 10ax squared plus a 5bx. Here's an ax squared bx plus c. And I'm going to get real emphatic here. This is a 1x squared minus a 1x. And dare I say, I'm even going to put in a 0 here because that's a full quadratic, isn't it? Let's just look at our x squared terms. And if we were to add all those up, we'd have a 4a, 10a, that's 14a. 1a makes a 15a. So we'd have a 15ax squared. Take a look at our bx's. Well, it doesn't take you too long to see we'd have a 6bx. And then we'd have a plus c. And you could call this undetermined coefficients or just call it coefficient analysis. You could say, hey, what's out in front of x squared? Well, a 1 on the right-hand side. So we'll have 15a is equal to 1. Take a look over here with 6b. 6b would have to equal negative 1. And we'll have that. And then finally, our c is equal to 0. So a is equal to 1/15. B is equal to negative 1/6, and C is equal to 0. So what was y sub p? Y sub p was ax squared plus bx plus c. That's 1/15 x squared minus 1/6x plus a 0. And then we link these two together. Final answer, c1x to the negative 1/2 plus c2 x to the negative 1 plus 1/15 x squared minus 1/6x. Done. And that